Welcome to the board. I want to start by showing you something that happens on our grid almost every day. We have perfectly good wind and solar farms generating cheap power, and customer demand is high. Yet we actively shut those farms off. When you see that happen, it's natural to assume our physical power lines are completely full. But the bottleneck isn't the metal itself. It is the rulebook governing how we measure it. Right now, we measure our grid capacity using something called static line ratings. Our operators must assume worst-case weather conditions at all times, specifically the absolute peak heat of summer, combined with zero wind to cool things down. The physics here is simple. Pushing electricity through a metal conductor generates heat. As the wire heats up, it elongates, and the whole line sags toward the ground. If that wire touches a tree or a structure, it triggers catastrophic faults, power outages, or wildfires. This extreme rulebook exists to protect public safety. We also have to consider the people enforcing that rulebook. The decision to limit power falls directly on the shoulders of the operational engineers in the control room. If an engineer allows extra power onto a line, and the line melts or starts a fire, the legal and financial liability lands right on them. This personal liability structurally incentivizes engineers to prioritize absolute caution over efficiency. They choose risk avoidance every single time. This leaves a massive gap between our cautious limits and what the wire can actually handle. This is phantom capacity, massive amounts of safe, usable energy that we are currently too afraid to transmit. A highly regulated infrastructure system cannot become efficient until we remove the fear of failure from the people running it. To bypass that fear, we have to move from assumptions to facts. We can use dynamic line rating, which uses autonomous LiDAR sensors to measure grid capacity as a telemetry-backed fact. The hardware is a self-powered unit that clamps right onto existing high-voltage lines. It doesn't require a power outage, making it a non-invasive upgrade. However, if we simply install these and demand immediate protocol changes, the organization's immune system will reject the data. Terrified engineers will naturally stick to the old, safer rules. Instead, we run a 30-day shadow test. We attach the sensor to a congested span and leave our standard operations completely unchanged. We just collect the sensor data in the background for a month. This shadow mode isolates the data from any operational liability. It creates a risk-free environment where we can prove the technology works before anyone has to bet their career on it. The sensor measures exact physical sag. It also tracks wind speed, showing how nature cools the metal. Combining these calculates ampacity, the line's actual changing power limit. Comparing this real-time capacity to our flat static limit reveals the phantom capacity delta. That highlighted gap represents literal, perfectly safe energy that the utility threw away every single day of the blind test. At the end of 30 days, we have an undeniable ledger of exactly how many megawatt hours were unnecessarily curtailed. This provides a clear path to financial recovery. We can see how much lost revenue the utility can reclaim without laying a single new wire. This shift also transforms our liability model. By relying on hard, real-time physics data, the telemetry carries the risk of the decision, lifting the burden off the individual engineer. This removes the fear of failure from the control room. It gives our operators their professional autonomy back and allows them to operate the grid at its true potential. This high-tech optimization avoids the traditional utility playbook of spending billions of dollars and years of construction on new transmission towers. Real technology does not replace people, it absorbs their risk and restores their capability.